used to analyze any kind of real world signal. Now from this lecture we are going to discuss discrete time systems, how discrete time systems are represented in time domain and how we can analyze them. So let's start with the definition of discrete time systems. Okay, the basic idea is that to process a given discrete time signal, we need discrete time systems. And discrete time systems will apply the required signal processing operations on a given discrete time signal in order to produce the required output. So every discrete time system will take a discrete signal as an input, which is essentially a sequence of numbers provided by our ADC, then apply some mathematical operations on those numbers in order to produce a discrete output, which will be again another sequence of numbers. So the thing to remember is that the input and output of each discrete system will have a discrete nature. No discrete system can generate or produce the continuous output. So this is the basic idea of a discrete time system. Here you can see we have applied x of n on this system, and x of n is representing a discrete input signal or an excitation to this system. And the system will apply required signal processing operations on the given x of n in order to produce another sequence of numbers at the output. So y of n will be considered as the output or the response of this system corresponding to the applied x of n. Now, what will be the exact shape of y of n? It will depend on the system characteristics, because y of n will follow that what exactly the signal processing operations we have implemented on it, or for what purpose we have designed this system. So depending on the system characteristics, we could have several possible shapes of y of n corresponding to the given x of n. Now let's come to the nature of this x of n. In signal processing domain, there are two options to process our signal, and those two options basically depends on how we are getting the x of n sample values. So if we are taking the sample values in real time and we are processing those samples in real time, then that particular system will be so called a real time processing systems. And another approach or option is that first take all the sample values and then apply certain signal processing operations on them. Then that particular system will be so called post-processing system or offline processing system. In that particular case, we will start processing our signal after capturing or after taking all the sample values of our x of n. While in the real-time processing systems, we are taking the samples in real time and simultaneously we are processing those samples through our system. So that particular system will be called a real-time processing system. Now, whatever the kind of system, whether it's a real-time processing system or a post-processing system, what is the ultimate target? We want to represent this system by a certain mathematical equation, or in other words, we want to develop a model of discrete time system which can relate y of n and x of n. So an equation which can relate y of n and x of n will be called the difference equation, and that difference equation will be considered as the model of our discrete time system. Or in simple words, that difference equation will represent the characteristics of system, and with the help of that difference equation we can calculate y of n or the output signal corresponding to any x of n. In real-time processing systems, we can apply signal processing operations on the live data or real-time data, while in the case of post-processing systems, we can apply operations only on the recorded data. And in recorded data, we can access all the samples of our signal because we have captured the whole signal, and then we are going to process it. While in the case of real-time processing, we can access only the present and previous samples of our signal which have already been captured and stored in our memory. So this is the basic difference between these two approaches of signal processing. Now let's come to the difference equation Difference equation is simply an equation which can describe a relationship between input and output signal of the given discrete time system. So difference equation can describe the characteristics of system in time domain because it can relate a discrete input and a discrete output signal of the given discrete system. And every discrete time system can be modeled or represented by using difference equations which can contain present values, previous values, or future values of the signals. In real-time processing systems, you will find we can use only the present and previous values of our signal, while in the case of recorded data or in the case of post-processing systems, we can also use the future samples of our signal because the whole data is given to us. And in every difference equation, you will find only three basic operations: addition of the several terms, a scalar multiplication, which is simply a multiplication by a constant coefficient, and the third or the last operation is the shift operation, which includes both delay or advance operation. So no matter what is the order of discrete time system, how much smaller or how much higher order of discrete time system is given to us, every difference equation will contain these basic operations, which includes addition, multiplication, and shift operation, which includes both delay or advance. Now, before moving further, let's take a quick review of the time delay and time advance operations. When we use a time delay operation, the basic objective is we want to access or to read the previous or past samples of our signal. So for that purpose, in order to access the previous history of our signal, we have to shift our origin towards left, or equivalently you can say a signal moves towards right. So if x of n is representing the original sequence, then its delayed version by k samples will be represented by x of n minus k. Now let's discuss the first example of a time delay operation. Suppose the x of n sequence contains these sample values and we have to delay this sequence by 2 samples, or to simply calculate x of n minus 2. So in order to calculate x of n minus 2, we have to shift this origin or reference point towards left by 2 samples. So after delaying it, x of n minus 2 will become equal to this one, where we have shifted the origin or reference point from this sample value to this one. So this will be the new reference point, or here we have to mark the origin because we are currently accessing this memory location. So the corresponding index value will be 0. Now, why this operation is said to be a delay operation? As you can see, the sample value, let's take this sample value which is 1 at -3 index. After delaying operation, this sample value is now appearing at -1 index. Similarly, this 4 sample value was present at +1 index before the delay operation. Now after delay operation, it is now appearing at +3 index. So this x of n minus 2 operation will be called as we have delayed the original sequence by 2 samples. Now, why we have delayed x of n sequence by 2 samples, or what is the meaning of this x of n minus 2 operation? The answer is we want to read or we want to access the sample values 2 samples before the current one is stored in our computer memory. And in order to understand this thing in more detail, let's take an example of both real-time and recorded data. This is the pictorial representation of the time delay operation in the case of recorded data. Recorded data means all the sample values of x of n have already been recorded or stored in the computer memory. And currently we are accessing this memory location where the sample value is equal to 3. Now if we want to delay this sequence by 2 samples, then what does it mean? As we discussed in the definition of time delay operation, we want to access the previous history or the previous samples of our signal. So if the amount of delay is 2 samples, it means that we have to address 2 memory locations before the current one in order to access the sample value. So after performing a delay operation, now we are addressing this memory location where the sample value stored is equal to 1. So the summary is, in the case of recorded data, we have an access to the previous sample values of our signal. And if the data is recorded, it means all the values of our signal are stored in our computer memory. We can access the previous values of our signal as well through the delay operation. Now let's consider the case of real-time data where the whole data of x of n or all the sample values of x of n are not given because we are taking x of n in real time. And in order to explain the idea of real-time data, here we have shown some sample values of x of n which have already been captured. And currently we are accessing this memory location where the sample value is equal to 3. Now with respect to this 0 index, these sample values will be treated as the previous values because these sample values have been captured at -1, -2 and -3 index. Now if we want to perform a delay operation on the real-time data, it means that we want to access the previous values of our x of n, and these previous values can be accessed only when we will store these values on our computer memory. So if we want to access the previous values, then it means we must have to store them on our computer memory. Now if we want to delay this sequence by 2 samples, then it means we are going to address this memory location, or in simple words, we want to address 2 memory locations before the current one. So in simple words, in real-time data, again we can access the previous values of our signal if those values are stored on our computer memory. And the thing to remember is that time delay operation is valid for both real-time data and recorded data, because in time delay operation we have to access the previous values of our signal, and the previous values of our signal can be accessed easily if we have stored them on our computer memory. So previous values could be available in both real-time and recorded data. And or in other words, time delay operation can be used in both real-time processing systems and post-processing systems. Now let's come to the time advance operation. Time advance operation means we are going to access the upcoming values of our signal or the future samples of our signal. So for that purpose, the origin or the reference point moves towards right, or equivalently you can say a signal will move towards left. So if x of n is representing the original sequence, then x of n plus k will be considered as the advanced version of the original signal by k samples, where k represents the amount of shift. Now let's consider this example of a time advance operation. This is our x of n, and we are required to advance it by 2 samples, or to simply calculate x of n plus 2. Now in advance operation we have to remember only one thing. We have to access the future values of our signal with respect to the current reference. So if the amount of shift is 2 samples for an advance operation, then it means we have to move ahead towards right by amount of 2 samples in order to address this particular memory location. So after performing the advance operation, x of n plus 2 will be equal to this sequence where we are addressing this particular memory location, or in other words, we have shifted the origin from this particular memory location to this one. So x of n plus 2 means we want to read the sample values 2 samples ahead the current one stored in our memory. Now let's take an example of both recorded data and real-time data in order to check are we able to perform advanced operation in these two types of data or not. So this is the case of time advance operation for recorded data. Since all the sample values of x of n are stored in our computer memory, which is the idea of recorded data, so with respect to this reference or with respect to this present value, these values will be considered as the previous one, while these values will be considered as the future values with respect to this reference. So in time advance operation, we have to access the future values of our signal. And if the amount of shift is 2 samples, then it means we are going to address 2 memory locations down in the computer memory. So after performing advanced operation, we will address this memory location where the sample value is 5. So in the case of recorded data, we can perform time advance operation because all the values of signal are already available in the computer memory. Now let's observe the case of real-time data. So this is the case of real-time data. Now let's see what will happen when we'll apply advanced operation for real-time data. If this is our x of n and we want to calculate x of n plus 2, so currently we are addressing this memory location, and for performing x of n plus 2 we are going to address such a memory location where no sample value of x of n is present, or in other words ADC has not provided or captured any sample value of x of n yet. So it shows that we cannot implement the time advance operation for real-time data. And the thing to remember is that time advance operation is valid only for the recorded data, because the future values of our signal will be available only in that case if we have recorded all the sample values of our signal prior to performing any signal processing operation. So time advance operation can be used only in the post-processing systems or offline processing systems. We cannot use the time advance operation for